All right, we're just continuing off where we finished on the last lecture, and we're going through given these half reactions here with the reduction potentials, and we went through and set up a series of equations based upon the oxidation, of iron 2 plus. So that's all set up in here by just two of the three substances. We decided to skip the third one, mostly because of space. We're on B now. For this one, we want to calculate delta G for each of the reactions that we listed up here above. So as far as establishing delta G, it kind of seems like it's out of nowhere, but we have done a problem previously finding delta G. And we can do that using this equation. So remember, this equation is established, and the purpose of it is to relate these two variables. There's not other weird things going on here. It just says, given this, what is this? All right, we have to backtrack a little bit here because in these two problems, we didn't establish what the cell potential was. So we have to go back and do that. And there's a couple ways we could think about doing this, but I think the easiest way is just remember, put it up here, that E of the cell is equal to the E, I'll call it, at the cathode minus the anode. And remember that cathode is where reduction takes place, gaining electrons, and the anode is oxidation, where electrons are being removed. So we have to take a look at these equations and say, okay, which is which? For this one here, it looks like the one that as far as gaining electrons is going to be the second one here. So for that, for the cell, E cell is going to be equal to positive 0.60 minus, it's a positive, I'm not going to write that down, 0.77. And the value for that would be negative 0.17 volts. The fact that it is negative tells me that this actually doesn't occur. It needs to be positive for this to be spontaneous. So this is telling me this is a non-spontaneous reaction. Fine, that's just what it is. For the next one here, again, same, the second equation is gaining the electron. So this one is written first at the cathode. So E for the cell is equal to, what do we have? It's something different. Negative 1.77 minus the positive 0.77, and that is going to be negative 2.54 volts. So this is even less spontaneous than the first one. Again, fine. Neither one happened, so this is disappointing, I suppose, but that's all it's after, is looking at that information. Okay, now given these two values, we can jump down and carry that forward into these. So I'm just going to list these as this is being 1 and this one being 2 is how I'm going to label them. So for the first one, looking at that equation that I have, I'm going to say delta G is equal to, I'm just kind of plugging in the information here, negative 2 moles of electrons that are exchanged, 96,485 joules. So I'm breaking down those units. Joules per volts per mole. And I'm doing this so we can get a meaningful answer at the end. Times the cell potential that I had from above, which is negative 0.17 volts. And if we go through and cancel out the units, we'll have an answer of 3.28 times 10 to the 4th joules, or 33 kilojoules for an answer. And that's what delta G is. For the next one, 2, grabbing the information from above again. As far as exchanging, we only have 2 electrons. So 2 moles of electrons exchanging place. 96,485 joules. So just kind of repeating this process from above. The voltage was different. So 2.54 volts, giving us a positive value again. And this was joules. Looking at my work here, I have a final answer, so I guess that would be 49 kilojoules if my work is correct here. Process is correct. I'm not sure exactly my answers, but I believe this is correct. So one thing to point out here again is the fact these are positive values tells me that this is not spontaneous. Negative values would imply spontaneity. And based on the magnitude, everything lines up. The more positive, the less spontaneous. And again, this is something we learned back in chapter 19. Okay, the last one on here, part C, we're going to use the other equation with equilibrium for this last part. Calculate the equilibrium constant K for the reactions above. So for this one, the equation we're going to use is delta G prime is equal to negative RT natural log of K. And again, this is all because we're at standard conditions. We can do this, no problem. Or because we're specifically looking for K, we have to manipulate this around a little bit. So we will just get it set up ahead of time is equal to E raised up to the negative delta G divided by RT. Okay, so the first equation, we're going to simply just plug in what we had from the previous problem and say negative 33 kilojoules. Now, I'm aware of the fact that I normally need joules here. So I can do this either way. What I'm going to do to compensate for that is take the R value, which is normally 8.314, and slide the decimal over 3 spots. So very important, you have to keep track of which units you're using and decimal places according to that. So 0.008314. I'm not going to bother to write the units in here, but this is going to be the R value with tons of units on it. Joules per mole per Kelvin, I believe. And the temperature. The temperature is, because I'm at standard conditions, it's 298. And if we do all this on our calculator, the answer is 1.6 times 10 to the negative 6. Again, the fact that this is a small number implies that it is reactant heavy and product light, so meaning it doesn't move in the forward direction very easily, pretty much non-spontaneous, and that's kind of what we would expect. For the second problem, E raised to the negative 4.9 times 10 to the second divided by 0.008314 times 298. And that will be equal to 1.3 times 10 to the negative 86. So again, not very spontaneous. Something I'll point out here, because depending upon which actual numbers and even significant digits you put in here, that's greatly going to affect your answer over here because of the E function. So really, the values do not need to be accurate so much as they are indicators of position. So in other words, I'm really not too concerned it's 1.3 or even that it's negative 86 exactly. The fact that it is negative 80 something tells me that this is incredibly reactant heavy. It doesn't move in the forward direction very well. Again, think products over reactants. This is very much reactant heavy. It doesn't move towards the products. And again, we see that reflected over here based on the delta G value and based on the voltage values. So all three of these kind of make sense together. Okay, this is a good place to end for this video.